So folks, in this section we're going to look at a spring mass problem. We've done some of these before, although the difference here will be that we have a forcing function. So in this case we've got a 1 kilogram mass that can stretch a spring, and we suppose that there's a dampening force equal to twice the velocity of the system that's opposite direction of motion. And finally we suppose that there's an external force. And this is what's new for these spring mass problems. We weren't able to put an external force on there before, but now that we have the method of undetermined coefficients, we can give it a shot. So as a reminder, our basic structure for the second order ODE for a spring mass problem looks like this. The mass times the acceleration plus the dampening coefficient times the velocity plus the spring restorative constant times the displacement of the spring. And all of that in our previous problems was set equal to 0, but in this case we've actually got a forcing function here, so it's set equal to 6 cosine t. So in our case what we have here is something, maybe let's imagine the problem like this, where we're going to have a spring, and let's set this up for the calculation. If I just let the spring sit here, this would be the equilibrium position for the spring, so this is 0. And if I attach this 1 kilogram mass to the spring, it stretches it. And these numbers aren't very realistic, but it keeps us from having to deal with decimals, and that's quite, or fractions as we find the roots of the characteristic equation. So it's nice to use these numbers. So the idea here is that when the spring is affixed, it stretches it. Or when the mass is affixed to the spring, it stretches it a distance of 10 meters. Okay. Then, just to add to this, the way we're going to think about this is that there's this external driving force. And so you can one way to imagine this is maybe you've got like an air vent here with a fan. And it's a very powerful air vent, and sometimes it forces air down this way, and sometimes it sucks air up, and that causes an external force on this spring. There's not really a good way to depict this, so what usually people will do is they'll just go ahead and put an arrow here with the forcing function equal to 6 cosine t. But this picture's always sort of bothered me when we just draw an arrow for a forcing function. It's not quite clear how we'd envision that, so that might be helpful to think about that. Either this fan is blowing the spring down or sucking air up, forcing the system upwards a little bit, and it alternates. Sometimes it's blowing downwards, sometimes it's sucking the air up, and that's reflected in that 6 cosine of t. Okay, so this is our problem, and we want to finish coming up with the ODE here. And in this case, well, a few of the things we were given. For example, we were told explicitly the mass was equal to 1. In some cases, we might have to solve for mass because we're given the weight of the object and not the mass. But in this case, we're okay. Also in this case, and usually I do this, the dampening force we were told that it is twice the velocity. Now, I don't really want to get into the signs on this. Everything was done initially for these problems doing a summation of the forces, and we were very careful with the signs, and then we set up the problem, and then we said, hey, when we do these problems, we'll always just assume m is greater than 0, b is greater than or equal to 0, and k is greater than 0. So the only thing we don't know, we know what mass is, we know what our dampening coefficient is, we don't know what the restorative constant is for the spring. So here's where we're going to use this information we were given, and if we imagine this scenario here, if we didn't have this dampening force and we just let the spring sit here, this is where it would want to sit, and we could then, it wouldn't be in motion, so we would say that the summation of the forces, just at rest, that the summation of the forces, which is supposed to be equal to mass times acceleration, would just be 0 here. And what are the forces on this spring? Again, imagining that forcing function is not there and it's just sitting at rest in this position. The forces on the spring would be mass times gravity, or the weight of the object pulling it downwards, plus the restorative force here. That was correct. Minus the restorative force there, so minus kx equals 0. And if we solve this, we get mg equals kx. Now, this is always a little bit confusing, folks. As I've drawn this, I've chosen an orientation here. 0's here, and so in this case, we're calling positive is in the downward direction, and negative is in the upward direction for our displacement of the spring. That may not be how you want to orient it, and you could go ahead and change the orientation there, but you'd have to make sure that you change everything when you do so. So it doesn't matter how you set it up, as long as you're consistent with your orientation. And I've thought of this as being a positive 10 meters as opposed to a negative 10 meters, and so then that means I would use a positive 10 for my gravity here. So in fact, I need to correct that to be a positive 10 for my gravity. So our mass is 1, and our acceleration due to gravity is 10, and we're trying to solve for that spring coefficient, but we know that this stretched the spring at displacement of 10 meters, and so we can solve for k, and we get k is also equal to 1. So now we're ready to give our ODE here, and we've got that 1 x double dot. Remember, the double dot just is another notation for the second time derivative, plus 2x dot plus 1x needs to equal the 6 cosine of t. So let's just write that again. X double dot plus 2x dot plus x is equal to 6 cosine t. And there's our ODE. Later on in these problems, I'll go ahead and give you some initial conditions to solve this. But for right now, there is our ODE.